Hello, everyone, and a very warm welcome to the inaugural lecture of Professor Alastair Donaldson. Ali joined us in November 2001. I think the hiring committee of the time is probably in full attendance. And I still remember, you know, how we realized this was going to be a catch if we can get him. And I think it's fair to say that, you know, this kind of prediction was fulfilled in any possible sense. He was promoted to Professor of Programming Languages in September 2020. As he will probably go into in his lecture, he's had at least 2 stints in industry. So we're very grateful that he actually returned to our department. I know for a fact that he cares deeply about the department. And he's perhaps one of those academics who has also a very deep passion for students. So he's very willingly exposing our first-year and second-year students to new programming languages, new concepts, exciting ideas, and willing to teach courses at those years, which is music to the ears of any head of department. And also, I think, you know, his research speaks for himself. He's an entrepreneur, a successful one, and, you know, he has a passion for other hobbies, which he is also exploring in this lecture. So without further ado, please, I want to hand it over to Ali to give his inaugural lecture. Thank you.
Thanks very much, Michael, for the lovely introduction. And it's wonderful to see so many old friends, students, colleagues, collaborators here today. It means so much to me that you've come all this way to be here at my lecture. As Michael said, I was promoted to professor in September 2020, actually, but for reasons we shan't speak of, it wasn't possible to hold an event like this until more recently. And what I want to do in the lecture is tell you a bit about some of my academic achievements over the years and the people who've inspired and mentored me. But rather than focusing solely on academia and computer science, I hope you don't mind me being a little bit self-indulgent and telling you about what I had actually wanted to do when I was growing up. Because if the teenage Alastair Donaldson could see me now, he might be a bit disappointed. When I was a teenager, computer science was not on the agenda at all, and for many years, it was only ever my plan B. What I want to do is tell you a bit about my plan A, and how Plan B, computer science, emerged from the ashes of Plan A. So, Plan A, I wanted to be a rock star, a world-famous, best-selling, stadium-filling rock star. As you can see, that hasn't entirely come to pass. But I like to think, and I'm going to try and convince you, that being a computer science academic is actually a pretty good substitute for being a rock star, because these seemingly very different careers have more in common than you might think. When I was 12 years old, my brother Hamish introduced me to the best rock band of all time, who are, of course, Queen. And from that day forward, I was intent on forming a successful band of my own. I was irresistibly drawn towards the drums, in no small part due to Queen's super cool drummer, Roger Taylor. And my parents very generously bought me my first set of drums for my 14th birthday. And this is actually the most flattering photograph I can find from that time. This led to the formulation of Plan A. Plan A was very simple. Step 1, form a band. Step 2, get a major record deal. Step 3, make a hit album. Step 4, do a sold-out world tour. And wait for it, Step 5, go to Step 3. So you can see there was some computer science here from the very beginning, albeit not the best practice of computer science. With my school friends, James, Andy, and Daniel, I formed my first band, Seraphim, and aged 15, we set out on our mission to take over the world, home recording demo tapes on a 4-track machine we borrowed from our school, and getting gigs in our home city of Glasgow and around the UK, wherever we could play. Let's hear a bit of Seraphim.
There's no defense, just a thin red line that knocked me out of space, blew me out of time. There's no defense, it's time to say goodbye. Where are the legendary pieces?
buoyed up by an unambiguous... Save it, there's more. Buoyed up by an unambiguous endorsement from our local newspaper, they sound like no one so much as themselves. We sent our demo tapes by mail order to tens and tens of fans around the world. One of our fans in 1999 boldly predicted that the year would belong to Seraphin. But sadly, 1999 didn't belong to Seraphin because our lead singer Daniel declared his intention to leave Glasgow, leading to the breakup of the band. This led to the conception of Plan B, computer science. I enrolled to study computing and mathematics at the University of Glasgow. Fully intended this to be a backup plan, I regrouped with my Seraphin bandmate Andy, and we formed the pop-tastic Acura together with Stevie, Shanky, and another James. Let's hear a bit of Acura.
Break the foundation of your dreams. Running for your life, waiting for time to get you. Be mine. But you'll never be mine.
Unfortunately, Acura was a bit short-lived. Despite sending our songs to every record label whose number we could get from directory inquiries, remember that? We didn't get any interest, and the band imploded. And this led to a bit of a dark time for me. I found myself in second year of a course I was only doing as a backup plan, with my dreams of rock stardom in pieces. But during that second year of university, I was taught by two inspirational lecturers who got me excited about my studies. In mathematics, Dr. Thomas Whitelaw, an eccentric but outstanding lecturer, brought linear algebra to life. And in computer science, Professor Muffy Calder bridged the gap between pure maths and computing in her functional programming course, where she told us about how to reason about programs using algebraic laws. This was my first inkling that maybe Plan B wouldn't work out so badly after all, and so started my journey towards computer science academia. In the rest of the lecture, I want to take you through the various stages of that journey. But perhaps because I'm still a little bit in denial about Plan A, I also want to draw some parallels between rock music and academia as we go along. In 2003, I enrolled at the University of Glasgow as a PhD student. And I would liken doing a PhD a bit like being an unsigned solo artist. You're unsigned because you're trying to prove yourself in your field of research for the first time, and you're a solo artist because you're doing it on your own. But when you're doing a PhD, you have a supervisor who is a bit like a record producer. You come up with the raw ideas, and they help you to refine them, prioritize them, and make them sparkle. And I'm delighted that my amazing PhD supervisor, Alice Miller, is here today. I learned so much from Alice about scientific rigor, concise writing, and Alice also taught me to take passion in an intrinsic interest of what I was studying. And in fact, one of the privileges of being an academic is that we get to study things because they are interesting for their own sake, as well as because they are useful and profitable. The title of my PhD was Automatic Techniques for Detecting and Exploiting Symmetry in Model Checking. Symmetry comes from my favorite area of pure mathematics, which is group theory, and model checking is a formal verification technique in computer science. Roughly speaking, a model checker is a computer program that analyzes another computer program to try and explore all of the behaviors of that computer program, either concluding that the program is correct or that it's incorrect, in which case a bug in the program is exposed. And techniques like model checking are really important in safety-critical domains, like the kind of software that runs inside cars and planes that you really don't want to go wrong. The main problem with model checking is that exploring all the behaviors of a system is often very expensive. It takes a really long time. But actually exploring all the behaviors of a system may be a waste of time if that system features many replicated components. Let's imagine we've got a program that features 5 interchangeable components. For simplicity, let's say those components can either be in a red state or a blue state. Well, if we've explored a state where 2 of the components are red and 3 of them are blue, that state is equivalent to a bunch of other states that also feature 2 red components and 3 blue components. So rather than exploring all these equivalent states, the idea of symmetry reduction is just to explore one representative from this class of states, which can potentially lead to a big saving. In this case, we're exploring one state instead of 10. My PhD work was about making symmetry reduction more automatic and more general. I've meant to say for the computer scientists among you, you usually apply model checking to concurrent or distributed systems, in which case the symmetry group that you use for symmetry reduction arises from the communication structure of that system. So for example, this tree on the right-hand side has got an interesting symmetry group called a wreath product. So I worked on making symmetry reduction automatic by using static analysis to work out the symmetry group of a system directly from its source code, and general, building a symmetry reduction engine that was capable of working with any symmetry group, leading to potentially faster model checking. Going back to my analogy between music and academia, one of the things that really attracted me to a career in music is the creativity involved in writing and recording songs. But actually, there's a tremendous amount of creativity involved in scientific research, especially at the early stages of a project, where you're brainstorming all kinds of ideas, and sometimes a really simple, elegant solution to a problem dawns on you almost out of nowhere. There's definitely something creative going on there. It makes me think of songwriting, where I like to experiment on the guitar or on the piano, messing around with various melodies until something that, at least to my ears, is magical emerges. Another thing about creativity is that when we write scientific research up, we have to be very creative. Now, don't get me wrong, I'm not suggesting we are creative and just make up the research, but actually if you've got a complicated idea that you want to get across in an accessible manner in a limited number of pages to your audience, you need to think very creatively about how to do that. And when I'm working on refining mathematical notation in a paper, coming up with snappy worked examples, it feels a bit like being at a mixing desk in a studio, perfecting a song and making it really work. I had a great time doing my PhD and knew that I wanted to carry on with a career in research, if plan A didn't work out, that is. But I wasn't sure what research problem to work on next. Seeking inspiration, I took a job in industry with a company called Codeplay, who at that time were very small, and they were working on compilers for multi-core processors. Inside your computer is a processor, and that processor understands binary code. But humans can't realistically write software in binary code. My uncle Hamish is here, and I think in the 1950s, Hamish probably did write software in binary code. But generally, humans write programs in higher-level programming languages like Java, C++, or Python. And those programs need to be converted into binary code. And the thing that does that conversion is called a compiler. And Codeplay specialized in compilers for multi-core processors, which are processors that have lots of parallel processing elements that can get many things done at the same time. The driving force behind Codeplay was Andrew Richards, who amazed me with his technical skills. He also looks a bit like a rock star. And two things I learned from Andrew with hindsight is the importance of self-belief and reinvention. It was incredible to watch him steering Codeplay's ship through the stormy seas of the multi-core world, constantly having to change what the company did by keeping one step ahead of what was happening in the rest of the industry. The most exciting thing I worked on when I was at Codeplay was a compiler for this device, the PlayStation 3 games console. Inside the PlayStation was a processor that was quite innovative at the time called the Cell, and the Cell was notorious for being really difficult to program. Codeplay were writing a compiler for an extension of the C++ language that promised to take away some of the pain of programming this device. The research inspiration I was looking for came to me when I was working on a data movement optimization in Codeplay's compiler for this processor. In the Cell processor, there was a large amount of main memory that was very slow to access, and then every accelerator core on the chip had a small amount of local memory, also called scratchpad memory, that could be accessed much more efficiently, but there was only a small amount of that memory. And the idea of the optimization I was working on was to figure out ahead of time some data that would be needed, so this data, bad food, and issue a prefetch to copy that into local memory just before it would actually be needed by the core. And then later on, there would be some more memory that would get fetched and consumed by the core. And most of the time, this worked out just fine. But very occasionally, due to a bug I'd introduced, unintentionally of course, into the compiler, 2 prefetch operations would be requested at the same time, leading to 2 chunks of memory being copied into the same portion of local memory, leading to garbage. I've illustrated here, bad for beef, because it's the beginning of bad food and the end of dead beef. But the point is that no one really knows what happens when this memory gets copied in simultaneously, and it tends to lead to something going wrong and the system failing. And what was really horrible about this kind of bug, which is called a data race, is that it only makes the system fail occasionally. Now, that might sound like a good thing. Surely it's better for a system to only fail occasionally than to fail all the time. But actually, it's a bad thing. If a system fails all the time, you know it's failed. And then when you fix the problem, you know it's fixed. But if a problem is intermittent, so that failures only occur now and again, it's much harder to work out what's going wrong, and really difficult to be confident you've actually fixed the problem, because the problem wouldn't happen a lot of the time anyway before you'd fixed it. I had a really stressful few weeks at Codeplay where I kept thinking I'd fixed this problem. I hadn't fully understood the problem, so I kept trying things and thinking I'd fixed it. And then someone else working on a different part of the compiler would come to me and say, Ali, sorry to be suspicious, but I'm seeing some really weird behaviors that I don't think can possibly be related to what I'm doing. I wonder maybe that bug hasn't been completely fixed yet. And this led to a really difficult time. So while being exposed to the horrors of data races wasn't fun, it was exciting because I realized that these are just the kinds of problems that model checking from my PhD could potentially be effective at getting a handle on. But no one had looked before on how to apply model checking to programs for heterogeneous multi-core processors like the cell. I'd found the inspiration I was looking for. But what about music and Plan A? Well, all the time during my PhD and Codeplay, I was pushing ahead hard with the most successful of the 3 bands I played in, Latonic. We built up a solid following in Glasgow and released a single that scraped into the independent music charts at number 30. Let's hear a bit of Latonic, and you'll notice I had a better haircut by this time.
Rockstar, broken heart, falling like a shooting star. Fucked up girl, killing you for who you are. Bad move, wrong turn, leaves you lost again. But turn on the side, thorn in my eyes. We'll turn it on, eyes open, eyes open. Again.
I'm really proud of what we did in Latonic, but by 2008, after 6 years of pushing very hard with this band, I think we'd run out of energy to keep up the momentum that's required if you're going to have any chance of making it in the music industry. And the band came to an end. Around the same time, my wife Chris finished her PhD studies at the University of Glasgow, and she persuaded me to finally move somewhere other than my beloved home city. With Codeplay's support as a project partner, I wrote an EPSRC postdoctoral research fellowship looking at applying techniques from my PhD, like model checking, which are formal verification techniques, to heterogeneous multi-core processors, like the cell. The fellowship application was successful, and I took the project to the University of Oxford. With no plans to start a new band, I immersed myself fully in computer science academia, and I had to admit to myself that Plan A had reached the end of the road, or rather, Plan B had become Plan A. Sometimes in the music industry, a record label will offer a band a development deal. This is where the record label don't want to commit to giving the band a full-blown record deal, but they're interested in what they're doing and are willing to put some money into supporting them to see where things go. My fellowship at Oxford was like a development deal. 3 years to do research with the goal of trying to get a permanent academic position. One of the best things about being a postdoc is that you don't have to do a PhD anymore. Now, I I have some PhD students in the room tonight, so I want to emphasize doing a PhD is great. But at times, you do feel a bit like Frodo Baggins with the Ring of Doom, the requirement to eventually write up 3 years' worth of research in a coherent way, weighing heavily around your neck. During my postdoc time at Oxford, I was able to collaborate with a number of different people on many shorter projects. This was like guest appearances, side projects, and collaborations in the world of music. I worked on symmetry reduction again with Thomas Wahl, who'd also done a PhD at the topic. I did a remote collaboration with folks in Australia on device driver verification. And I continued to work a bit with Codeplay, writing some papers on the most innovative things about their compiler for the cell. But the highlight of my time at Oxford was working with a fellow postdoc, Philip Rummer, on my main project about applying model checking techniques to heterogeneous multi-core software. I had my industrial experience of the problems of data races in these kind of processes, and Philip had a strong background in symbolic verification, which is a different kind of formal verification to what I'd done during my PhD. Philip suggested that a technique called K-induction might be a good fit for the problem domain, and together we produced a solution that allowed automatic detection or automatic proving of the absence of the kind of bugs that had plagued me during my time at Codeplay. My mentor at Oxford was Professor Daniel Croning, from whom I learned many things, but two things that stuck with me are, first of all, that you don't need to give up programming if you want to be a successful academic. I absolutely love computer programming. To me, it's the most creative thing I do in my job, and it's actually quite like playing a musical instrument. But I'd assumed if I was to have a successful career as an academic, I would need to do less and less programming as I got more senior. But Daniel showed this needn't be the case. Despite being a successful professor with a sizable research group, he was still the main developer behind CBMC, a very well-known model checking tool. The other thing I learned from Daniel was academic ambition. He was determined his research group would publish at the top places in the verification field consistently. And he once said to me, if you're not getting at least 50% of your papers rejected, you're not aiming high enough. That brings me to my next analogy between the world of music and the world of academia. In academia, we get reviewed all the time. Our papers get reviewed, our grant applications get reviewed, and our teaching gets reviewed. And especially in the case of grant applications and papers, we get lots of rejection. It's very common to have things rejected. Likewise, if you want to try and make it in the music industry, you have to get used to rejection after rejection from record labels. And even if you do make it as a successful band, you're inevitably going to get some cutting reviews from the jealous media. Here's an example of a rather negative review from one of my papers from a few years ago. This work has serious problems. Lack of novelty, substantial issues are brushed aside. Evaluation actually makes the case the approach is not viable. This kind of feedback is never easy to take, even when it's fair. But luckily for me, I'd had harsh feedback from the age of 15 when I started trying to make it with Seraphim. Let's look at an early review of a Seraphim demo from a fanzine called DDDDDDD. I had to blank out some swear words up there. It says here, this demo just is not very good at all. 4 guys with the regulation rock instruments doing tuneless stuff, which even the new style beautiful South would spurn. So in the world of music and in the world of academia, you have to have a thick skin, and as Andrew Richards taught me, a lot of self-belief. Luckily, my career has not all been about rejection, and in 2011, I was successful in applying for a lectureship at Imperial College London, which has been my academic home ever since. For me, this was the computer science equivalent of the major record deal. Since joining Imperial, teaching has become a big part of my job, and as Michael said, I'm really passionate about teaching. I enjoy it just as much as research. One of the best things about teaching is getting to engage with enthusiastic, bright students at Imperial. But if I'm honest, one of the things I really like about teaching is I get to be in the spotlight. I get the thrill and excitement and responsibility of trying to make stuff accessible to the audience, engage them, inspire them, and I get to use my technical skills and try and make sure I don't mess up. In short, like a professional musician, I get paid to perform. I've worked on a bunch of different projects in my time at Imperial, but I want to tell you in a little detail about 2 of them that have been particularly important for my career. They are GPU Verify and Graphics Fuzz. A graphics processing unit, or GPU for short, is a massively parallel accelerator. I told you earlier about multi-core processors like the cell, which have a handful of distinct processing elements, or cores. But GPUs have hundreds or thousands of parallel processing elements, so they can compute a vast amount in a short space of time. They were originally designed for computer graphics and are still used for computer graphics, but they've now found application in many other domains like machine learning and computer vision, and they're one of the enablers of self-driving cars. I was interested in looking at the problem of detecting data races, those concurrency bugs I'd looked at in my Oxford postdoc days, in the context of GPU computing. But I realized pretty quickly that the techniques that had worked well for multi-core processors just wouldn't scale up to the massive parallelism present in many core GPU processors, and that a smarter approach would be required. My team and I spent quite a long time thinking hard about solutions and looking for something that would scale, and we realized that actually, despite the enormous amount of parallelism, the GPU programming model is pretty simple. When you program a GPU, you orchestrate a number of threads that run in parallel. Here I've called the threads T1 up to T8, but imagine there are thousands of them, not 8, and the parallel bars indicate that they're executing at the same time. If you would like the threads in a GPU program to synchronize with each other, you have to use a barrier operation. And a barrier forces every thread to wait at the barrier until all the threads get to the barrier. And then they can all proceed after the barrier. And in the GPU programming model that's most widely used, the only way for threads to communicate is via a barrier. So if T2 wants to consume data produced by T1, there needs to be a barrier separating the production of the data, the write, by T1, from the read of the data by T2. In particular, it's not allowed for threads to communicate with each other without there being an intervening barrier. And we realized that the simplicity of this programming model would allow us to get a handle on the problem of trying to prove race freedom of GPU programs. And we built a technique called GPU verify that works by taking a massively parallel GPU program and exploiting that simple programming model I mentioned to turn it into a sequential program, a program with just one thread of control. And this transformation is done in a clever way that ensures the following theorem holds. If the sequential program is correct, by which I mean no assertions can fail for the computer scientists here, if it can be proven that the sequential program is correct, then it follows that the GPU program is free from data races. And the good thing about this is that while proving properties of sequential programs is still not an easy task, there's been decades of work on that problem. So by turning the massively parallel program into a sequential program, GPU verify can then leverage all the research that's been done on reasoning about sequential programs. In principle, you could plug in your favorite verification tool for sequential programs here to handle the resulting program. And in particular, we used Boogie from Microsoft, but in principle, something else could have been used. This project was quite successful and led to a bit of industry adoption. ARM, the processor company, incorporated the tool in their Mali graphics debugger, a debugger to help people using ARM Mali GPUs. And we took GPU Verify on the road. Many people contributed to the project, but in particular, Nathan Chong and Jeroen Ketema, who were in my research group for a while, did a lot of work on GPU Verify. And the three of us went to many different conferences, workshops, and summer schools teaching about the technique. And while not quite the sold-out world tours that I dreamed of in my childhood, one of the privileges of being an academic is you do get to travel, you do get to see the world, and you do get to make friends in lots of other countries. So that's another thing that the careers have in common. I've talked quite a lot about compilers in the lecture so far, and the next project, Graphics Fuzz, I want to tell you about, is about compiler bugs, what happens when the compiler goes wrong. As a programmer, we strive to write correct computer programs that are going to do the right thing. And we might use tools like the GPU Verify tool I told you about to try to show that the programs really do what they're supposed to do. But remember that the processor, whether it's a regular CPU or one of these GPUs, the processor consumes binary code, and a compiler has to produce that binary code. But the compiler itself is a computer program. So if the compiler is defective, then we may end up getting incorrect machine code, by which I mean the machine code program doesn't actually do what the source level program is meant to do. When we would give talks about GPU Verify on the road together, we would often get asked the question of, what about bugs in the GPU compiler? And a friend of mine, Anton Lokhmatov, who I'm delighted is here today, said to me, Ali, I think you should go and do some research into GPU compiler correctness. He alerted me to some promising work on testing C compilers. And I'm really grateful for this advice from Anton, because it led to a long line of work on compiler testing by various people in this room that ultimately led to the graphics fuzz project. I'm going to cut to the chase and tell you about graphics fuzz. Suppose you've got a graphics program, a program designed to run on a GPU. That program needs to be compiled before it can be given to the GPU, and then it will eventually run, and it will produce something on the screen, a nice pretty picture. And if there's a bug in the GPU compiler, the wrong picture will get rendered. But the trouble is, unless we know exactly what the right picture is, we can't know that the wrong picture has been rendered. If we want to intensively test a graphics compiler, we'd have to have a whole load of programs for which we already know what the expected image is if we're going to find that the compiler deviates from that expectation. This is called the oracle problem, and it's a difficult problem in software testing. In graphics fuzz, we get around the oracle problem using a very simple technique. We produce from an original program a whole load of transformed programs. And we do this by randomly applying transformations that have a special property, which is they preserve the semantics of the program. Whatever these transformed programs look like, they're guaranteed to produce the same image as the original program. So the idea is that from the compiler's point of view, these programs look very different. There are lots of different opportunities to optimize them and maybe mess up while trying to optimize them. But ultimately, we should get the same stack of images produced for all the programs in this family. And if we see a deviation, we know there must be a bug in the GPU compiler. And the clever thing about this, which is called metamorphic testing, is that we still don't need to know what the right image is for this program. It's probably the majority, but in principle, it doesn't have to be. The fact that we see different images from programs that should produce the same image means something is wrong. This very simple idea, which was inspired by previous work called equivalence modular inputs testing from researchers at UC Davis, worked very well in the graphics domain, and we were able to find bugs in practically everything we touched with graphics fuzz. We found bugs in all sorts of compilers from GPU companies across the industry. We found a security vulnerability that affected Apple devices that Apple acknowledged and gave us credit with a CVE related to this bug. And a couple of the members of the team, Hugh and Paul, and I got so excited about this, we decided we wanted to see, would people pay for this technology? Are they just happy that we're finding bugs and reporting them, and they go, oh, great, thanks for telling us. But after a while, we didn't want to be free testers for these companies. We wondered, would people pay for this technology? So we formed a startup company of the same name to try and commercialize this technology. This really felt like being in a band again, as did taking GPU Verify on tour with Nathan and Jeroen. It was so exciting working with Hugh and Paul, phoning each other up all the time with ideas, producing demos of what we were doing, trying to work out what we should implement next based on what this company wanted, what that company wanted, what that company wanted. Thankfully, Google came along and made our life simpler by buying the company, which leads me to the sellout. In any rock music career, a band has to have a point where they sell out. And in September 2018, we sold graphics fuzz to Google. And the three of us joined Google as part of the acquisition deal. I retained a part-time position at Imperial College London. The reason Google were interested in graphics fuzz is that Google make the Android operating system, and graphics is a significant component of an Android device. But although Google make Android, Google don't make very many Android devices, phones and tablets that run Android. In fact, a lot of people don't necessarily know that a Galaxy phone is an Android device. They may think of that as a Samsung device, a Galaxy device, not necessarily an Android device. But there are all kinds of companies out there making Android devices. And to try to make sure those devices work well enough so that Google can be proud of the Android brand, Google require companies to pass the Android compatibility test suite if they want to be officially qualified as Android. The Android compatibility test suite is like a barrier between end-user devices, your phones and tablets, and bugs that could potentially affect those end-user devices. Bugs can only get to your end-user devices if they don't get caught by the Android compatibility test suite. But the problem is that testing is never going to be able to get rid of all bugs. So there are chinks in the Android compatibility test suite's armor. And what we were doing is using graphics fuzz to find those bugs ahead of time and improve the CTS, the compatibility test suite, with tests that would kill those bugs and stop them from making it through to end-user devices. When I was at Google, they were very sympathetic to me still having one foot in academia. And in 2020, I had the pleasure of being the general chair for PLDI, the Programming Language Design and Implementation Conference. This was going to take place in London, but because of the pandemic, we had to make the conference virtual at very short notice. While that was a really stressful experience, a good thing about it was it gave me a chance to try my musical skills out again. My friend and collaborator, John Wickerson, had the idea that to tell people we really are running the conference, albeit in a virtual form, we should make a promotional music video. And he wrote fantastic lyrics to the tune of You Were Always on My Mind, called This Is Still PLDI. And we roped our computer science friends into singing on the video.
This is still PLDI. This is still PLDI. This is still PLDI. This is still PLDI. This is still PLDI.
Google is a great company to work for. I'd really recommend working there sometime in your career if you can. But compared with being an academic, it's not as creative. You don't have as much autonomy. And not doing as much teaching, there's not as much chance to perform. In short, being at Google didn't feel as much like being in a band as being in academia. Which brings me to the last chapter in my story, come back. I was delighted to be promoted to professor in September 2020, and in February 2021, I rejoined the Department of Computing full-time as an academic. And since then, I've been rebuilding my research group, enjoying teaching new courses, and getting stuck into some exciting new research. And the final project I want to tell you about is a collaboration with my former colleagues at Google. I've talked a lot about compilers during the lecture. Remember, a compiler turns a source program into binary code. When you're learning to program, you normally learn from examples, tutorials, informal sources of information. You maybe try things out by seeing what a compiler does. But when you're making a compiler, you need to do a slightly more rigorous job. You need to look at the rules for the programming language. These come in the form of a language specification, which ideally should give semantics to every conceivable program that could be written in the programming language. At Google, I worked a lot with a programming language called SpearV, which is a language designed for graphics programming. I'm going to show you an excerpt from the SpearV specification. I don't want you to read it in detail. I just want you to note that it's got this section about structured control flow, and that it says structured control flow declarations must satisfy the following rules. And then there are several pages of rules. In this language, these structured control flow constructs are designed to let programmers communicate information to the compiler that can allow it to emit very efficient code for the GPU. And in principle, that's a really good thing, and SpearV is an exciting language. But unfortunately, these rules about structured control flow were pretty ambiguous and vague in places, and programmers were having a hard time using them. Here's an open source developer being sarcastic on Twitter saying, targeting SpearV is super easy, and the structurization requirements, that's the control flow, totally won't make you want to throw yourself off a cliff. This looked exactly like the kind of problem that could benefit from a formal treatment. So in this piece of work, my team and I took the informal, ambiguous SpearV language specification, and we made a best effort mathematical model of the control flow features of this language. And the great and horrible thing about mathematics is it's completely unforgiving. You can't be ambiguous in mathematics. So this was an ambiguous specification. We had to make a model. So where the specification was ambiguous, we had to make a best effort guess at, is this what they meant? Let's try it and see. And then we would talk to experts at Google who knew a lot about what the industry wanted from this programming language, and we would go to them with particular examples and say, what about this? What about that? And they would tell us what they really wanted, and we would refine the mathematical model and iterate this process many times until we reached the point where the model, we believe, was completely precise. spelled out exactly what the language designers wanted. And then we took the mathematics, which is pretty heavy going, and we used it as the basis for rewriting the language specification using crisp, precise English prose. And earlier this year, the language was updated to reflect the changes that we proposed through this modeling exercise. I'm really excited about this paper, which has just been accepted at the POPL conference, which is the other main conference in programming languages. I'm excited because this collaboration between Imperial and Google epitomizes the kind of research I love to do, that brings together fundamental computer science techniques and difficult, important industrial problems. So to sum up, it's been a pleasure to have this exciting academic journey, and I'm really honored to have been promoted to professor at Imperial College London. Thanks for listening to my plan A, which, to quote Ian Jury, if it had worked out, might have involved a lot of sex and drugs and rock and roll. Instead, my plan B has more been about hex and bugs and flow of control. But it's been a real adventure. Thank you very much. Before I take your burning questions about Seraphin, I just want to say a few thank yous. First, I want to thank my incredible colleagues at Imperial College London, all of them, but especially the 3 heads of departments during my time here. Susan, who saw promise in me and hired me. Daniel, who helped me transition from full-time at Imperial to part-time during my time at Google. And Michael, our current head of department, who welcomed me back last year. I want to thank Christian Kadar, who was a few steps ahead of me at Imperial and in whose footsteps it's been a pleasure to follow. Philippa Gardner, who was my academic mentor when I joined Imperial and has continued to give me very valuable advice and guidance since then. Paul Kelly, who persuaded me to join the university, gave me the courage to apply, and he's been a constant source of wisdom. And my friend and collaborator, John, who as well as being a great musical buddy, is one of the most pleasing people to do research with, and I'm sure it won't be long before I'm sitting at John's inaugural lecture. We're lucky to have a brilliant operations team and administrative team at Imperial led by Anne O'Neill, who's done a fantastic job during all my time at Imperial. And I'm really grateful to all the financial, secretarial, HR, administration, our brilliant computing support group, and the events team. And for this lecture particularly, I'm especially grateful to Lucy Athis from the Department of Computing and Meg Carter from Imperial events team, who've made this a really special occasion for me. Can we thank them? I've used the word I a lot during the lecture, but all the work I've told you about was done with collaborators. I'm lucky to have a brilliant research group at the moment, and I've had fantastic students and postdocs pass through my research group in the past. And I was going to do a list of all the people I've ever written papers with, but I just ran out of time because there are so many of them. They've all been amazing. So I'm really grateful to all my co-authors, collaborators, and project students. Okay, and now the part where I'm definitely going to get emotional. I want to thank all my family and friends all around the world for... I cry when I watch Strictly Come Dancing and MasterChef, so you don't need to feel embarrassed for me. All my family and friends around the world. My brother Hamish died in 2003 at the very start of my PhD, but I really want to mention him because he introduced me to such great music at a young age, and he was so proud of our family. And I think if he could be here now, he'd be so chuffed to know that I got made a professor. My brother Jerry is here today. Jerry, thanks for being the best listener in the world, for taking an interest in all my bands, coming to so many of my gigs, and listening patiently when I told you probably more than you wanted to know about computer science. My parents, Julia and Malcolm, are still living the dream, and they gave me so many opportunities when I was growing up and took my outlandish dreams of rock stardom seriously, and have always supported me with whatever I wanted to do with my career. My gorgeous children, Poppy, Felix, and Kitty, bring me so much happiness every day, and they put things into perspective. When you get a paper rejected, there's nothing better than going home to some young children who don't know or care what a paper is. And more than anyone else, I want to thank my amazing, incredible wife, Chris. We've been together for 20 years this month, and she supported me through thick and thin. And she helped me a huge amount prepare this lecture. So Chris, I've told you about plan A and plan B, but our lives together with our children is better than anything I could ever have planned. Thank you.
Ali, thank you so much. I think on behalf of all of you, I'm probably entitled to give you a hug. Yeah, this is really great. Thank you. Thank you. So this was a very inspiring, and compassionate lecture, and I think it raises the bar for all the colleagues in the future who want to deliver something like this, which is good, So I think we have some time for questions. Maybe we should take the first one in the audience, in the lecture room, and then go to some of the online ones. Any questions in the theater, please? Yeah, over there. Just wait for the microphone, please. Also the subsequent question.
Right, so I guess I have one. That would be, have there been any cases, during your career where you were thinking, oh God, I have no idea what I'm doing. Please, Mom, come pick me up, I'm scared.
Absolutely. And what I've learned is that that's normal. Everyone feels like that. People get up and give these talks where they talk about their successes. Wouldn't be that interested if people gave talks about all their insecurities and failures. But we all have them. Being an academic is competitive. That's another analogy I could have drawn with the world of music. And yes, there are many times in my career where I haven't really known what to do, haven't been sure what I'm doing. So that's very normal and very common. And I guess my advice to anyone in that position is just keep at it, keep talking to people, get feedback. And just like that thing I said about experimenting with a musical instrument, things come to you after a while. Sometimes it just takes time.
Sure, so it's my pleasure to voice some of the questions that have been asked online. And I think the one to start with is this one. Which rock star would make the best computer scientist?
Oh.
Which instrument would they play?
I know which rock star makes the best physicist and astronomer. Of course, the main reason I came to Imperial College London. I know that the bass player John Mayang from Dream Theater has said publicly he probably would have become a computer programmer had he not been in Dream Theater. So I think him.
Thanks. Is it, I think Andy?
Yeah, thanks, Ali. I just wanted to ask, so I understood how graphics fuzz tells you whether there is a bug, but to what extent does it help you to find where the bug is?
Thanks, Andy. Yeah, that's a great question. What graphics fuzz does is it takes the original program and it applies loads of these transformations at random to give you the transform program. The problem is that transform program looks like gobbledygook to a human. But we know it gives a different result from the original. And we made the transformations. So graphics fuzz has an automatic reducer that through a kind of trial and error process that's known as delta debugging, tries to work out the minimum sequence of transformations that causes the deviation. That doesn't actually say what the bug is, but it provides a really good starting point for a compiler developer to do debugging.
Okay, so the next question, I'm going to combine a couple of different questions. People are very interested in selling your company, becoming obviously fantastically rich, and coming back into academia, which is not necessarily a recipe for riches. And I think to kind of turn that into a question from the audience, from Naman Sharma and others, tell us a little bit about how you stay motivated, where your creativity comes from, given that story.
Yeah, thanks. I think for me, I probably wouldn't have gone into academia in the first place if I was particularly financially motivated, because I think we get paid a respectable amount of money, but it certainly don't get paid nearly as much as you can get going into industry. And I feel like life is precious and life is short, and you need to seize it and do what you really want to do. And there's a common phrase in industry, golden handcuffs, which is where a company always give you more shares if you stay a bit longer. And if you love what you do, that's a win-win. You have more money and you love your job. But if you think, and of course it's a win-win if you need money to buy a house, you need to get to a milestone in your life, something that would maybe change your children's lives, that's totally understandable. But if you get to the point where you think, I'm not that happy with what I'm doing, or it's okay, but that other thing would be much better, there's the potential that the golden handcuffs will mean that you don't make that happen. And then, you will be older and have more regrets. So I felt like I could have, I want to reiterate, I really enjoyed working at Google and I would really rate it as a place to work. But it became clear to me after a while, I would just be happier and more fulfilled if I returned full-time at Imperial. And I decided to take less of the money that I would have made being at Google to come back because, it would have been extra years of my precious life.
Lucky us, yeah. I think we have one last question in the lecture theater and then maybe one online. Anyone? I think Sophia, maybe?
Thank you, Ali. A wonderful talk, as usual, actually. I was very intrigued about the last project that you described, and I think in some sense it's different than the previous ones, because with the previous ones, you found wonderful techniques that could automate the process. And with the last one, you were in the process all the time. So I'm wondering, in the next iteration, can you imagine automating some of it? You would not want to only do it for, I don't remember the name of the programming language, but there are many, many, many that suffer from such fuzzy, bad...
Yeah, I think that's a great point. So we put an enormous amount of work into trying to fix this programming language. And while I'm really proud of that project, and it's been a success, if we were to try to work on another programming language, we would just have to put an enormous amount of work in. Sure, we would benefit from some of the experience, but we couldn't directly reuse any of the technology we built for that language. So what I would really like would be to have, and there are people who are doing work along these lines, I really like the idea that you get a lot of bang for your buck if you go formal. So you write down a language formally, and as well as getting confidence in the prose document describing the language, you maybe get for free a reference implementation of the language, perhaps a program generator if you want to test optimized implementations. Maybe there are other components you can get from that formal description of the language implementation, rather than doing a kind of ad hoc, best fit for this language, best fit for that other language. The problem I see is that sometimes generalization can make specific details hard to get a handle on. So our SPIR-V model is very detailed. There's a lot of devil in the details, and it's not clear to me how viable it would be to come up with a more general framework. But yes, I think that would indeed, that's my main criticism of my own work in that case. It's very focused on that one language.
Maybe the last question from the online.
So actually, I think we don't have more questions from
online. Okay.
Rather, I think we've covered most of them.
Okay.
But what I would say from watching the online comments is a lot of people out there are appreciating your talk today from all over the world. And we have comments from Paris, from Oxford, from Sao Paulo in Brazil, and lots of online applause, joining the applause that you've heard today.
Thanks to all of you online. I really appreciate you being there.
Thank you very much. I think this is the right point in time now where I can invite Professor Alice Miller to come to the stage and deliver the vote of thanks. Thanks very much, Alice.
Well, first of all, I want to say thank you to Alastair for inviting me to come and have this very honourable job of thanking you for the talk. As Alastair mentioned in his talk, I was his supervisor at the University of Glasgow, and Alastair was my first ever PhD student. We had a little laugh about this earlier on, that you never give anybody as much attention as you do to your first PhD student. And so they probably think that that was normal, but obviously it's not. So obviously I've had quite a few PhD students since then, and they've all been fantastic, but they always refer to Alastair as Saint Alastair. And roll their eyes slightly whenever I mention him. When Alastair was at Glasgow, he worked very closely with Muffy Calder as well as myself, and she had a PhD student at the time, Douglas Graham, and we were quite a little team, and we were very proud of them, and they were both these tall, sort of good-looking young men, and sort of very, very vivacious and very intelligent and very sort of engaged in what they were doing. And we were very, very proud of them at the time. Apart from the one night when they went out of an evening, I won't go into too much detail, Alastair. And Alastair decided to give the bouncer at the club a little bit of lip. And I think you've probably never done that again, have you, Alastair? But, so it's been wonderful to have this opportunity to see you flash through your career, because when you hand over a PhD student, you don't necessarily get to see what happens to them afterwards. And I've very closely followed Alastair's career, and I'm immensely proud of what he's achieved. And it's extremely brave of him, I think, the fact that he's combined this work in industry as well as academia, and he's come from one thing to the other, but he's always been extremely driven and really clear in what he wants to do and what he wants to achieve, and I think that's so admirable, and we could all learn from that approach. So anyway, I don't want to take up your time, because I'm sure, like me, you're desperate to get to the bar. But and I expect Alastair is extremely desperate to get to the bar. But it's been wonderful to have the opportunity to meet your family. I've met some of you in the past. I've probably met most of you, apart from the ones who weren't born at the time. But I met quite a few of you at Alastair's wedding, which I was very, very privileged to be at as well. But hopefully I'll get a chance to catch up with you all later on. So you can really sense the warmth in the room for Alastair, because he's just made so many connections throughout his career, and he's obviously very much part of this Imperial family, and I'd like to congratulate him again on his professorship, and all the best for the future.
Alice, thank you very much for this warm vote of thanks, and I make sure I'll sit next to you at dinner so I can get into some of these details a bit further. So this now concludes the formal proceedings, and there will be a reception out there, and just enjoy the rest of the evening, and thank you so much for coming in the room and also online. Thank you very much.